Record. I'm on it. I was prepared. Today is the 5th. Let me get that up there for you. Today is 12/5/22. And you're going to learn about 3 things today. They're all, I hope, pretty basic. Ooh, fingers crossed. The first one is called the counting principle. The second thing that we'll talk about are permutations. And then the last thing to conclude will be combinations. So we're knocking a lot of stuff out here today. So if you encounter any difficulties, as always, please speak up. So first off, let's talk about the counting principle. And the counting principle allows us to answer questions about like how many different ways can you get something done? So an easy example would be, let's say you go to a sandwich shop. And I always just please understand that I dumb these way down. Like there's all sorts of like time wasting. Let's see if I can get class off track questions. So try to keep those to a minimum. I'm purposely just simplifying scenarios to kind of tie them in here. So let's say you're at home and you're going to make a sandwich, and you're going to make a sandwich with bread, meat, cheese, and vegetables. That's fine with me. But the assumption here is that you're going to pick one of each. And so let's say you have 4 types of bread in your pantry. And again, I don't want to have weird discussions about all this stuff, so just kind of hold that off. So we have 4 types of bread. Let's say you have 3 types of meat. So presumably like turkey, chicken, ham, something like that. And then let's say you have 2 kinds of cheese and 2 vegetables. So presumably like lettuce and tomato. And again, there's all sorts of way tangential sort of let's waste time conversations, but let's keep it simple. So if I'm going to make a sandwich and I'm just going to pick a type of bread, a type of meat, a type of cheese, and well, should we have condiments as well?
Yeah.
So how about like 3 condiments? So if I'm going to make a sandwich where I'm going to pick a bread, a meat, a cheese, a vegetable, and a condiment, just one of each, then the counting principle says that there are, let me do the math real quick, 12, 2, 4, 48, 144 sandwiches I could make. And do you guys want to guess as to how I got that? It's actually not a factorial. I wish that it were. Good guess, though, but it's not a factorial. I did. And the counting principle simply says this, that if you have options along the way, you simply multiply the number of options at each stop. And so I look at it and I go, okay, so I have 4 breads to choose from. So I'm going to put 4, and then I'm going to put times. And then I have 3 meats to choose from. So I'm going to put times 3. And then I've got 2 cheeses to choose from. And then I've got 2 vegetables to choose from and 3 condiments to choose from. And if you multiply those out, that will always give you the number of uniquely different sandwiches that you can make. This is not necessarily a permutation. It's not a combination. This is why I'm teaching this lesson in 3 parts. This is something called the counting principle, and it is just that easy. So you just probably want to use a calculator, but we just go left to right. 4 times 3 is 12, times 2 is 24, times 2 is 48, times 3 is 144. So if you were going to make a sandwich with one of each of those things, there are 144 different sandwiches that you could make. All right. Another simple example would be something like, let's say you have 4 pairs of pants and 7 shirts. And you were just simply going to randomly go in there and grab a pair, grab a shirt, boom. How many outfits could you make? The answer is 28, which is 4 times 7. Okay. I mean, if you wanted to make a sample space and look at it, you could. I don't necessarily want to, but I do want you to just see kind of how it would start. So let's say that your pants were like red, brown, black, and what else? Khaki. Sound good? What did I put? Was that a blue?
Black.
Black.
Red, brown, black.
Khaki. And then for your shirts, I mean, this was a terrible example. Let me pick something a little bit simpler. Listen, the bottom line is your sample space would look like this. Like you would pick one of your pairs of pants. So you might pick like your black pair of pants and your red shirt. You might pick your black pair of pants and a blue shirt. You might pick your black pair of pants. The bottom line is if you looked at it out, you'd see that there are 4 pairs of pants. And off of each pair of pants, there could be 7 shirts that come off it. Like, have you ever seen like a tree diagram? Yeah. It would look like one of those. Yeah, it kind of actually starts to look like that, right? How about this? Let's say this one will be easy to make a sample space for. So let's say you flip a coin. And then roll a die. So what would be the number of possible outcomes here? 8. It took us a while to get there, but thank you. Yes, it is indeed 12. How many things can happen when you flip a coin? 2. How many things can happen when you roll a die? 6. So this is a good one to show you what a sample space would look like. So, and I showed you this a little bit last week. So if I were going to make a sample space out of this, I could say, okay, the 2 things that can happen when I flip a coin are heads and tails. And then the 6 things that can happen when you roll a die are 1, 2, 3, 4, 5, and 6, right? And so a sample space would be something like this. I could get heads 1, heads 2, heads 3, heads 4, heads 5, heads 6. And I hope this kind of illustrates the idea of why sample spaces or why the counting principle works the way it does. Because I could also get tails 1, tails 2, tails 3, tails 4, tails 5, tails 6. And I think that's a real good visual way to kind of understand, hey, look, 2 times 6, there's a column of 6 and a column of 6, 2 columns of 6. Seems like a no-brainer. So that's what the counting principle is applied for, is generally saying like, okay, if I can do this, then this, then this many different ways, I simply multiply them together to get the total number of things. Okay, you'll see some questions about that. And they're obvious. They're obvious on the homework. It'll say like, Orgo has 5 pairs of pants, 6, la, 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 la. When you see one of those questions, then you're going to know, is that one of your phones blowing up or is that, would you please shut that vibrate thing off? It's literally vibrating up into my bones, my forearm. I'm going to need surgery to fix the carpal tunnel syndrome. What happens? You getting blown up? You getting tweets, texts, Instagrams? Snapchat. Can someone please just blow up Snapchat? Let's talk about the next thing. Permutations. This one, it can be a little bit interesting. So. Yeah. If you're not careful here, then watch out because this can get confusing. So just stay with me and it won't be confusing. Okay. So for permutations, we're going to put a little comment next to this. It's the number of ways things can be arranged. And there's going to be a confusing formula here in about a couple of minutes, but I'm going to hold off on that. So you remember the problem that we talked about Thursday, and I know that dragged on for a while, but when things like that happen, you just got to let it go. You know what I mean? Just ride with it. We talked about if 17 of us in this room were going to be arranged for a photograph, we figured out that it would take like 16,500 years or something. And it's hard to believe, but the math is pretty hard to dispute. So that's a permutation for the record, because if 17 of us are going to be lined up for a photograph, every time, like if Kale's on the left and Colby's next to Kale, if Kale and Colby switch places, that's a new permutation. right? If Luke and I switch places, that's another permutation. So every time two people switch or three people switch, every time you're coming up with a new order, that's another permutation. So what I want you to add to your notes here is that with permutations, order matters. And you'll know the difference between problems. Most often, if you're not sure, ask me. But if the problem is written relatively well, you'll know if order matters. Like you can tell if it's a batting lineup, does order matter? Of course it does. You don't have to be a sports fan to know that like who bats first and who bats fifth. That matters to baseball coaches, right? If we're conducting student senate elections, does order matter? Maybe. I mean, I think it does. Is it different if someone wins president and someone else wins vice president? It does. I think order matters, doesn't it? Right?
Yeah.
Can you think of a time when order doesn't matter?
When you buy cheeseburgers, which one do you eat? Making your sandwich?
Can someone ask Brandon to put his phone away? Oh, thanks, buddy. Good.
You go to try with food, you pick all the options,
The fact that you're saying you don't know which one you're going to eat first tells me that you do then say that order still matters. An example of when order doesn't matter is if you say you won 4 tickets to the Super Bowl and you got to choose 3 people to go with you. The order that you call your friends in doesn't matter. Like if I win the trip and I decide that I'm going to take Kelton, Eli, and Luke, I'm just taking a group of 3 people. The order of them does not matter. You follow? That's just literally picking a group of people. When we talk about permutations, order is everything. The sequence in which I pick them or the sequence in which I place them or the whatever, that's a permutation when order matters. So let's go back and revisit our question from Thursday, only we're going to do it on a smaller scale. So let's say that a classroom has 10 students. And they're going to arrange themselves for a photograph. This will be a more reasonable but equally kind of mind-blowing sort of answer. If you have 10 students in a room and someone walks in and says, I'd like to take photograph of all 10 of you, but I would like to see you in all possible arrangements. Does anyone remember from Thursday how we would figure out how many ways there are to do that? 10. It's actually not that. And it is. And what's interesting is if you think of the people lined out, you got person 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those are the blanks where the people can stand. That's like my photograph ready to go. When everyone is still sitting in their seats, how many people could I choose to stand on the left? I'm sorry, that came out wrong. I have 10. Again, that was my bad, poorly phrased question. I have 10 people from which to choose. And let's say I pick someone. I say, hey, Fred, you go stand on the left. Now I only have 9 people left. And once I pick Fred and then I pick Sally, I've only got 8 people left. And what am I writing as I do this? Yeah, and I do want you to get used to using that word. I'm using a factorial. So if I wanted to know how many ways 10 people could be arranged for a photograph, I would simply do 10 factorial. And do you guys want to know a secret? Your calculators have factorial buttons. Some of you already figured that out?
No, I asked to show it on the
If you guys have TI 30s, let me show you where they are. If you don't have a calculator, you should certainly assess when it's like middle of December and you still haven't done that. Do you guys see the button that says PRB?
Yeah.
On a TI 30, it says PRB. If you're on a TI 84, yours is going to say math. Hit the math button and then go into the PRB menu. Do you see it? So if you're using a TI 30, if you hit PRB, do you see how there's an option over there to the right for factorial? The exclamation point? Don't do NCR or NPR. We're going to use that later. Do you see the factorial sign? So if I type 10 factorial into my calculator, it comes out to what Brandon said.
Dude, that's not near as many as.
Of course it's not. But think about like how much of a difference it makes. If we added just one more person into the mix, now we have to take this times 11 and so on and so forth. So if there were 10 people in a classroom and you wanted to take their picture in all the possible different arrangements, there would be over 3.5 million ways to do it, which still would take, well, suffice it to say, a very long time. Are we all comfortable with that? Not talking about your calculator not having the button. Are we comfortable with what I mean by that?
Yes.
Okay, then let's move on. Because the heart and soul of today's lesson is not just that. It's not just about you hitting the factorial button on your calculator. I'm going to take this down a notch, and this is where I really need you to pay attention if you've fallen asleep. Wake back up. Now, someone's going to walk in the room, and there are 10 students sitting there, and they say, I need a photograph, but I only need 4 of you. It's actually a very simple concept, and I'm going to show you a couple of different ways to do this. Number one is to draw a picture. So again, someone from the yearbook staff comes in and says, hey, this is Mr. Ahern's third hour. I want to take a picture, just a sample of the class. I just need 4 of you to come out here. So if we have 10 people and we're going to take a photograph of 4 of them and we care about the order that they stand in, I can still make blanks, but I'm only going to make this many. Because if you think about it, now think hard, that makes sense because that's what the photograph's going to look like, right? There's just 4 people in the photograph.
Mm-hmm.
How many people does the yearbook person have to choose from for their first person?
10.
They do. And then they pick another one. How many do they have to choose from? Another one? Another one?
7.
So you would agree this is like an abbreviated factorial. This is like a factorial that kind of goes, I'm going to stop because I only need 4 people. You can do this on your calculator. Yes.
There you go, 10 times 10 times.
Yes. And I don't know if Sam was trying to be sarcastic or not, and I think that your question was legit and Sam pointed out the obvious that yes, you could just type it in. But is there a formula for this? Yes, there is. So if I had 10 people and I wanted to arrange them 4 at a time, I always had the option to draw a picture like this and then work it out. 10 times 9 is 90. 90 times 8 is 720. And 720 times 7 is 5,040. So there are 5,040 ways to arrange 4 people picked from a group of 10 for a photograph. Got that? I'm going to show you a formula now.
Do you have that memorized or
I just did that. I'm going to show you a formula. You ready? And you definitely need to write this down. It doesn't stand for National Public Radio. This is a permutation formula. Your calculator will do this for you. Ready? The formula for NPR goes like this. On top, you put n factorial, and on bottom, you put n minus r factorial. Put your calculator down and write this down. Because I need to know if we go no calculator mode that you're going to know what this formula is. We'll do a lot of this on our calculator. It is not. So get this copy down and then I'll explain to you how this formula applies to this particular problem. So P obviously stands for permutations. N is, I'm going to put little arrows here and you can copy these into your notes. That's the total amount. So like in this, in my example, N would be 10 because we had 10 people in the class. And what do you guys suppose R is?
Mm-hmm.
Nope. It's the group size. And so if someone walks in with their camera and says, hey, I just need to quick snap a picture of 4 of you, then N in this case is 10, but R is 4 because we're having 10 people, but arranged only 4 at a time. So the way my math problem would have looked for you guys is, take a look over here. We would have set this math problem up as 10P4. That's what it would look like. 10 people being permutationed, if that's a word, 4 at a time. So in this case, N is 10. So what would go on top of my factorial formula up here?
10.
Nice job. And then on bottom, you just got to do like some third grade subtraction. What is n minus r, or 10 minus 4? It is. So I'm going to put 6 factorial on bottom. And as you saw the other day, you now know how this works. You'll see now, I hope, why we did that other worksheet before we did this one. And I start working this out. How do I do 10 factorial divided by 6 factorial? Well, I start writing and I go 10 times 9 times 8. And when do I stop? After the 7, because all the stuff I'm about to write is exactly the same as the stuff I would have written on the bottom. And it still comes out to, well, 5,040. Got it? I did
Oh, I see.
10 minus 4. Good. Let's practice. I'll come show you. They're not going to give you serious answers. I'll come show you. I promise I will. I will. Is that an old TI-30? Okay. Because if it's an old model, it might be a little bit rough, but don't worry. It has it. I'll just need to figure out how to make it work for you. Nice. Let's do another one. Let's say we have the same situation. So let's do our class. So let's say like today, since Chance is gone, there are 17 students in this room. So let's say we have 17 students. And instead of taking a photograph of all 17 of us, let's take a photograph where order matters of 6 of us. So yearbook staffer comes in and says, hey, I need 6 of you. I want a representative sample of third hour intermediate algebra. I need to take a picture of 6 people. How many ways can we take a photograph of 6 people out of 17?
11. Well, 11. What?
It's 11 with the 8,900,000.
And how did you get that?
I put it in.
Good, good. So option 1 is if we know now where to find the NPR, we can type it in like that. Option 2 is to utilize the formula. Remember, this is N and this is R. And so I'm going to do N factorial. So 17 factorial over, what is 17 minus 6?
11.
Very good. And so and I'm teaching this with the assumption that someday, I don't know, maybe you're trying to do it on your phone and you just have a calculator that doesn't do it for you. So then when I start writing out my 17, I go 17, 16, 15. And when do I stop? After the 12, right? Because then I'm aware that everything after 12 would just be a duplicate of what's going to be on the bottom. So if you haven't found it yet, if you were there, you saw it. There's literally an NPR button inside of this. And so when you go back into your probability menu, go ahead and type in 17. And then go into your probability menu, your PRB, choose NPR. And your screen should now say 17 NPR, and it's waiting for your R value. It's saying, okay, so you're telling me you have a group of 17 items. You're going to arrange them. How many would you like to arrange at a time? And that's where the 6 comes in. So you hit 6, hit enter, and that's where Brando got his 8,910,720. Would we have gotten the same thing if we just multiplied out what's up on the TV, those 6 numbers? Yes, we would. And if I'm doing any semblance of a decent job today, then you understand that method up there on the board is our go-to sort of, I hope it makes sense if I don't have a fancy calculator on me method, right? Because then I could use any calculator, like out of a box of Frosted Flakes, to do 17 times 16 and so on and so forth, right? So that's permutations, and that's again, that's when order matters. The last part of this, I'll try to make this quick, is we're going to now talk about combinations. All right? Yeah.
Is that NCR?
It is NCR. Yep. So continue, please take notes. Give me about 3 minutes of just writing, no calculators, and then we'll get to the calculator part. So the last part of this, and then we'll do some worksheets here, is combinations. And for this, we're just going to say something like picking groups. And so remember in the last one I told you with permutations, I underlined it. And what did we write underneath there? Do you remember? Order matters. What do you think we're going to write under this?
Order doesn't matter.
Order doesn't matter. So in a case like this, I know I'm working with a combination problem when the order in which things are placed is of no significance. So an example of that is, again, like I said, with Eli winning tickets to the Super Bowl, and he can pick people to go with him. The order in which he picks them is irrelevant. And another example could be that yearbook person comes in and says, I need a picture of 6 of you, but the order doesn't matter. So like if it goes, you know, this, these 6 people in a row, they're not going to say, okay, you guys switch places, and you guys, I just need 6 of you. Boom, get back in the room. That becomes what we call a combination problem because the items are just being combined into a group. We don't care who goes first. Okay? These are significantly more difficult to understand. The permutations are very, very visual. You can see with those blanks, I have this many people that can go here. This combinations are harder than that to understand. So let me give you the formula, and then we'll get our calculators back out. So just like NPR, there's a formula for combinations, and of course, as you know, it is NCR. And just like before, N stands for the total. Like that's your big main class size or big group size. And then R is your little kind of group size. And the formula for this one is very similar to the formula. And there's going to come a day, depending on how long we spend in this unit, where what I'm about to write will actually make sense, believe it or not. But the formula for this is n factorial over r factorial times n minus r factorial. It is an extra thing. And if you're really paying attention today, you'll notice, I'm going to erase this in a second, but you'll notice that this part that I put in the green box, isn't that just the permutation formula? It is. And then what? Just practice. Yes. No, I know what you mean. Like the mechanics of practicing canceling. Yes. So what happens with this is, since order doesn't matter, when I pick things out of a group, I don't have to rearrange them over and over and over again. Once I get a group of people, I go, thank you very much. We're done here. Say we had 4 letters. I want you to write this example down with me. They are A, B, C, and D. And we're going to pick them 3 at a time. It's exactly what it is. How many combos of 3 can we do? So if I feel like it's logical that the first combo that I would pick, if someone said to me, hey, pick 3 of these, sorry, this is just how I roll, I would pick a combination of A, B, and C. Good. What else could I pick? And I'm going to try to be organized about this. So I could pick A, B, C. I could pick, I'm going to keep with the A, B theme here. I could pick A and B, but then I could finish it off with D. What else could I pick? B, C, and D. Is there any other combination that I've overlooked?
D.
I've already got DCB. It's right here. It's DCB because it's a combination and I don't care about order. Are there any other?
CD.
There are not. Now, if order mattered, oh, you're right. I don't have that one. Thank you very much. I don't have ACD.
Bad.
Say again? I've got BAD right here. For you guys who are looking for new combinations or new arrangements, you're just not listening. I don't care about the order, but thank you for catching ACD. I overlooked that one. But BAD is not unique. I've already got A, B, and D in a group, right? Now, could I arrange each of these groups? Sure, but I'm not going to because this is just a combination problem. But if someone told me to arrange them, then I could do ABC a lot of different ways. I could do ABC, ACB, BAC, BCA, CAB, CBA, but this is just a combination problem, so there are only 4 that I can choose from. So let's plug this into the formula and see if it's legit. So our formula tells us, in this case, if I've got 4 letters, that N is 4, And what would R be?
3,
Good job, because we're picking them 3 at a time. So what would go in the top factorial?
4,
So 4 factorial, and what goes in the bottom?
3 factorial times
Good job, Brandon. 3 factorial times 1 factorial. And so you can see why the answer is, so let's write it out. 4, 3, 2, 1, 3, 2, 1, 1. Cancel stuff out. And as we would expect, when this 3, 2, 1 and this 3, 2, 1 die, you can see that there are 4. Okay. Do you feel okay with this? There's 2 formulas, and I realize that a lot of you are probably just like, let's move on with this, because once you know there's an NCR and an NPR button on your calculator, I get where you're at. In your mind right now, you're like, bring it, I can do this. But again, behind the scenes, this is what's going on, NCR, and then the NPR is exactly the same without this extra factorial on the bottom. Okay. I'm going to say this just because I won't sleep tonight if I don't. I was trying to get away and not say this because I see Luke falling asleep here, but I'm going to do this anyways. Can you guys help me right now rearrange these 3 letters and then we'll be done? I got to sleep peacefully tonight. I'm going to A first. Keep A first. ACB. Now I'd like all the ones that have B first. What are they?
BCA,
Now I'd like all the ones that have C first.
CAB,
I'm going to sleep so much better tonight. And if this gets through to 5 of you, I'm going to feel elated. How many items are in this list? How many items are in this list? And what is 3 factorial? And that's why this works the way it does. I wasn't even going to bring this up, but I decided I got to do this. If in each of those columns, if you took one of the little groups and you arranged it all the possible ways by switching to a combination instead of a permutation, that's why we divide by 6. Because instead of 6 of these, I only need to acknowledge 1, and 6 divided by 6 is 1. So what the combination formula does is it eliminates redundancies. It says you've already given me ABC, that accounts for ACB, BCA, BAC, CAB, and CBA. That's where that comes from. So I have 2 worksheets for you today, and I'm going to hand them both out. I think they're broken down like one of them is all permutations, and I think the other one's all combinations. And then once we get good at this, then I'm going to start giving you practice problems where you won't know which is which. What's that? Yeah, let's do that. I'm going to stop this first.